everybody. This is Andy Lamora. You've probably seen me online as B-Chops. I've been with Topcoder since 2005, and today I look after, from the business and practice point of view, our data science and AI business. We're talking to you today about the famous lung tumor challenge. We ran this from 2017 to 2018 with Harvard Medical School. There are a lot of names involved in here. The actual stakeholder and the credit for challenge, a lot of the challenge formulation and making all this possible went to the Laboratory for Innovation Science at Harvard, known as the LISH. And Rinat, Dr. Rinat here worked for LISH at the time we ran it. This was a three-part series, as some of you might remember. And today we'd like to spend quite a bit of time actually talking about the problem itself, what went into it, what was really at stake with the solution, and what you guys did to solve it. So let's jump in. We're beginning with a picture on the right of a cancerous lung. So let me share with you one thing that came out of this project loud and clear after working personally with a lot of these stakeholders. Don't smoke. Seriously, if you're smoking, please try to stop. Lung tumor is lung cancer is a nasty, horrible thing, and if you get it, it's pretty tough to treat, as you'll see here in a minute. What you're looking at there on the right is emphysemic, is probably a smoker as well, but the tumor is that whitish nodule at the top of the lung. At the end of the day, what we are trying to do with this challenge is to eliminate that tumor without surgery. Kind of exciting. So here's what we're covering today. We're going to go over what lung cancer is because it's necessary in order to understand what the challenge had to do. We'll go over how lung tumor treatment works today, what Dr. Ray wanted to do about it. We'll talk briefly about the data. We'll spend quite a bit of time on the challenge approach, and Dr. Sergeyev is going to walk us through some stats on the results. The lead investigator for this was Dr. Raymond Mack. He's a medical doctor with joint appointments at the Harvard Medical School and this country's, the United States, one of the United States leading cancer institutes. He is a Harvard Medical School professor. Also joining us, as I said, is Dr. Sergeyev, who is the senior scientific advisor on this. And there are many other people who contributed to the problem, and you can learn more about them in the JAMA article. We'll share links to that. Okay, to set up our story, let's talk a little about data science overall. If you're a data science enthusiast at Topcoder, you know that we post challenges around just about every domain there is, whether it's algorithm optimization or using statistical approaches for forecasting or machine learning for really hard problems. Over the last couple of years, the community has produced some just phenomenal results with practical outcomes. And a lot of the techniques that we see here apply both to things that make oil and gas safer and less pollutant, and in curing cancer. So it's an exciting place to be. As everyone knows, any data science problem is really a research problem. It always goes through a couple iterations. There's always a certain amount of time that's spent trying to figure out what problem to solve, like the quadrant we have here on the left. You discover the information that you've got, and you define the types of problems you can answer on. You define the problem that you actually want to tackle, and then you go and develop a solution on that problem. And then you do it all over again as you learn more information. And the way that those things get done are increasingly, as I'm sure this audience knows, a blend of a few different things. Way back in the day, it was just people. You had people who really knew how to solve problems and would come and work on the problem. Then you had open source libraries that started making it easier to work on them, platforms too. And together, and increasingly folks look to platforms to say, can I just hit a button that does something? All of these elements came into play in solving this problem. So it was really exciting to see. So let's begin with lung cancer. Here is a nasty lung. This patient had emphysema. There's the cancer that you see. And the scale is, the picture is not drawn to scale here, but A tumor can range in lots of different sizes. And as you can see here from this image, a lung tumor is a really tricky thing. You can't just take the lung out of a person, especially if it's bilateral, right? You have a tumor in both the left and the right pleura. So it's necessary to have techniques that allow you to remove that tumor without having to remove the lung or a lot of the tissue around it. Lung cancer is super bad. It's 14% of all the cancers and 25% of all deaths. So it's a very tricky thing to serve, as especially illuminated here in 2012. This data is a little dated now, but in 2012, 1.8 million people were diagnosed with it and 1.6 died of it. So obviously this is a snapshot of 1 year, and that 1.6 is reducing as the efficacy of treatment increases. But it's a major, was and is a major problem. It's much larger than all the, much more lethal than most of the other types of cancer. The way it's treated today is with radiation. So it's one part of a multitude of therapies that a physician might take. If it's a really bad tumor, they might try to surgically remove it. If it's impossible to remove, like for example, if the tumor is growing right by the spine, then they'll turn to chemotherapy and radiation. When we say radiation therapy, this is what we mean. That machine there is a LINAC machine. It's a linear accelerator, and it shoots radiation in as narrow a beam as possible into your tissue. It tunnels into your tissue and burns out the bad stuff. So it's a big, expensive machine. And you can see this is basically how it works. The machine rotates around the patient and shoots a bunch of radiation into the patient. And why is that? Well, the answer is because you don't want to have the same beam go over the same territory twice. And we'll get into that. The way this machine is run, though, the input to that machine is this: a CT scan with a bunch of borders drawn on it. This is the delineation, and segmentation. So the net out of it is drive one of these machines with a bunch of these pictures. And that ultimately was our task. Here's how this generally works. You take a CT scan of a patient. It develops a bunch of slices of images. If you stack and interpolate all these images, you get a 3D picture of the patient's thorax back, and you see that on the right. You got a patient's model right there. A physician has to go in and manually delineate each one of those tumor traces in order to feed it into the machine. And here's somebody doing exactly that. A doctor looks at each and every slice and with a mouse delineates that tumor. You can see what that delineation looks like on the right here. Typically, they're going to do the tumor, and then they'll do a couple borders outside of it, which basically are fencing to say, don't go beyond this. And it takes about 30, well, for a small tumor, maybe as few as 10, but 30 to 60 minutes. It takes a long time to do this. And the other thing to point out with this is that it's not easy to do. They're not just looking at a pixel and then drawing a line around it. A physician today really needs to understand the human anatomy in order to do this. They're applying a mental model of what normal tissue should look like. While they look at it. So what a physician's really doing is they're looking at a 2D slice and then imagining where that 2D slice would appear in a normal representative volume of the patient. Then they apply normal. What would normal look like? And then they ask the slice a question: where are you not normal? And then after deciding that a piece may not be normal, they then ask a second question, which is, what are the reasons why you might not be normal? Because, hey, it may not be cancer. All right, somebody might have a structural deformity, or there might be a congenital thing there. It could be some kind of deposit. So a physician's applying all of that thought to decide whether or not something is a tumor. And it takes about 10 years to be good at this. And mind you, this is lung tumor. So we're not even talking about somebody who might also be proficient at pancreatic tumor or something else. This is just lung tumor. So it takes 10 years to get good at lung tumors. And once you get good and you trace it out, this is then when radiation comes into play. You see here the figure on the right that shows the beam trajectories of that Rinat machine as it rotates around the patient. That little dot you see, that contoured nugget in the center, is the tumor. And you have multiple beams. We're showing 3 here, but you have beams that will then go through the patient and they intersect on the tissue that you want to kill. The way a physician will say it is the tissue that you want to dose with radiation. So why don't you send a beam of radiation into the patient the first time that would be lethal to the tumor? Because it would be lethal to all the tissue that is in the path of that ray. And so you would just burn a hole right through a patient. In order to avoid that, you send multiple rays instead that have sublethal dosage that intersect over one point and deliver the lethal dosage to that. So you're trying to kill the cells in the cancer. One heck of a problem to solve. So obviously, accurate delineation of the tumor is really important. And that, everybody, is why this is a machine learning problem. Because you'd be justified to say, well, if you've got all these grayscale images, how come you can't just apply a computer vision type approach to this and say, you know, pixels that are surrounded by this pattern that have this grayscale value are cancerous? And the answer is because it's not always cancer. So while that kind of technique obviously does provide some benefit and some use, it has to be coupled somehow to these 10 years of experience that people have. And that brings us to what this challenge was. Bring in data that isn't just your CT images, but the delineation that these experts have performed on them in the past, and try to learn from repeated patterns of behavior of top flight experts, in addition to what you might learn from computer vision. So here are some problems today with tumors. There's a lot of variation. If 2 doctors are working on the same volume, there could be only about 70% agreement between those 2 doctors on that same volume. And in fact, even the same doctor might segment it differently on a different day. It's just not that easy to do. You know, there are a few reasons that are cited here. Data overload is one, limits of what you can detect in the grayscale is another. And, you know, by the way, 10 years of learning, and that's, you know, already normalized on a really, really intelligent and sharp group of people, right? Access to care can be something. And now here's the other thing. The same doctor that's doing the treatment is the doctor that has to do the segmentation, and is the same doctor who's seeing the patient. That means that the doctor is spending 30 to 60 minutes of their patient time with a computer instead of with the patient. And at the end of the day, doctors are here to heal. And Dr. Ray made this point repeatedly. It's like, I want to treat my patient. I don't want to just play a video game. So there's a lot more that a doctor can be doing to help a patient get better. So the solution is, can you automate this delineation step? Can you create something that allows a doctor to more consistently trace out this tumor and spend a lot more time with their patient, and in so doing, cure more patients? That's the end. That was the end goal of this. Create AI that cures more patients. But there's a second element to this too that Dr. Ray doesn't specifically call out, so I'll add it here. Rural, remote, and frankly less wealthy areas might have access to hardware. You might be able to fly a patient to a machine. But what you probably don't have access to is Dr. Ray. And this is a lot more than just access to a Harvard doc. What we really mean here is particularly in areas that are sparsely populated, you might have an oncologist that is looking at patients with all types of cancer. There aren't enough patients in that area to specialize in lung tumor because they're seeing a lot more of prostate or breast cancer or other things. And as clearly shown in the research and as the data we walk through here, it takes 10 years for somebody to get good at lungs, let alone everything else. So what's really at stake here is, can you create an easy button? can you create a button for physicians that lets them answer the question, what would Harvard do? And then let that become input to the physician. They may choose to accept it. They may choose to create their own trace. But in any case, they will be able to see what Harvard docs would do. And cutting to the chase, y'all succeeded. So let's look at the data. In this challenge, we had CT scans as input. We were given, we had from an earlier, or the researchers had from an earlier study, 461 patients with CT scans with a median of about 157 images per scan. Of those scans, we had, breaking it down, it meant that we had just shy of 78,000 total images, of which 8,000 had pictures of tumor in it. So this was not really a challenge to diagnose cancer. That's what's important. It's a really important thing to know here. We knew that, contestants knew that it was that somewhere in that set was a cancerous image. So we were focused on treatment, not on diagnosis. We reserved 229 scans for the training set. These had the contours that were provided by more than one physician, and it included the physician's comments in case that would be useful in the contest. All of these images were scrubbed for PII. They came to us as DICOM, and we converted them to, I believe, medical TIFF. And we also provided a visualizer for this. Our co-pilot, who was awesome on this thing, created the image you see on the right. The way the docs work with these volumes is by scrolling them forward and backward, and seeing if, seeing structure develop throughout them. We needed to replicate that experience. So part of what Topcoder does in the challenge setup is to pay attention to these types of problems and make sure that you've got the tools you need in order to solve the problem. In that case, this involved creating a visualizer, as you see here. And in addition, that visualizer allows you to see the contours that were created. And we built the scoring function into it too, so you could see when you're competing how you were performing in a code snippet, in a data snippet against the scoring function. So great work from the co-pilot on this stuff. Okay, let's get into the challenge. So this wasn't the kind of challenge where we post one and hope for the best and we're all good. This was a marathon challenge. We're going to spare some time here and won't go into what the differences are between the different challenges on Topcoder. We're just kind of assuming you're aware of it. But if not, check out the site, check out Thrive, and you can find a lot of information about marathons. In this challenge, we knew that we were going to have to run a few. The first step was to just see how much could be done in one pass. It began with two tasks. Find the find the tumor in the volume, and then contour it. So again, the contestants were allowed to assume that one existed, which obviously is an important feature of the challenge. But here's the issue with the special challenge here, no pun intended, with lung tumor. They aren't always just a blob. They are sometimes more akin to, imagine a paper bag, blow into it, and then crumple it up. So you might have hollows that you're not going to dose. You might have big folds where the tumor goes around the spine. The spine's not a great thing to kill. Please don't kill the spine, right? So you have to stay clear of that. Or they might go around the heart. The heart's pretty important too. So these volumes are not continuous spheres. They're loaded with folds and hollows and volumes, and we knew that'd be a problem. So the first challenge aimed at locate the tumor and do the initial contouring. The second phase of the challenge was, okay, now let's improve, the high level is let's improve the accuracy. But what we're really doing is find the exact, find the borders of the hollows and of the complex folds so that you're not, so that you don't miss them. and then phase 3 was a private invitational where we invited people to collaborate and work towards that goal. Dr. Rinat, would you like to add anything to this?
Absolutely. Andy, thank you very much for providing the Topcoder view on the background of this project. I would add a little bit of the view from the Harvard side. So there are several components that actually made this project very interesting. And so the first of it that we and I'm still the visitor at the leash, so I haven't completely cut that connection, and I'm very proud of that part of my my academic history. So we have been a very unique lab that was very open to the most exciting processes in the world. We are trying to figure out what can this world do different. We got very unique partners like on Ray and on Harvard Medical School. It was Yevaginen, who was heavily participated on this project, who were extremely knowledgeable in their area, and they were open to the idea of do something better. And then we had probably the best partner in the world, the Topcoder community, which we knew by that time for at least for 7+ years, and participated in multiple unique projects and achieving great results in those projects. So that we knew that can do a lot of something really special. So it can do, it can solve the problems better. We already had examples when the Topcoder community had been solving problems way better than the experts, and something great could be achieved there. So the whole idea was what can we do with that combination overall? When we have a lab that knows how to do innovation, but we have no idea how the lung cancer works. We have the lung cancer specialists who know everything in their area, but they don't even know what, they are open to the ideas, but they don't even know what can be improved. They don't even know what is right and what is wrong, whether what they're using good, bad, can be improved, and what is even that component that can be improved with. And we know that Topcoder can improve basically everything, but we don't know exactly how to frame that and to apply that to that area that we use. So even before we started this project on Topcoder, we went through multiple rounds of framing the problem on, hey, we have those 3 unique resources, we're putting them together, what can we solve? So the first answer was they're gonna save the world. So then we kind of framed it a little bit, okay, let's just save the world within our expertise. So we found the expertise, okay, so the lung cancer is important, and there is definitely some technical problem that could be potentially improved with machine learning. But when we go into details, you don't even, it's even hard to know from the beginning what exactly in that problem can be potentially improved. And this actually, so this idea of hey, we don't know what can be improved, where we can get great results, but we know that somewhere on the way we are going to get them. So that resulted in this multi-stage approach when we wanted to kill the 2 rabbits in the one type of framework, when we both wanted to frame the problem and to solve the problem to the greatest extent. So if there had been 3 phases you can see on this image, but in fact there were 5. So there was the first phase when we basically said, hey, here are the images from Ray that he personally annotated. He spent a lot of his personal time to annotate, to segment those images and sort of verified. And that's also by the greatest images segmented by the greatest radiologists. That's a good data set. So it's also pretty hard to get to get due to all the privacy and other concerns. So what can we do? Like first idea was, hey, just like here's the images, can you reproduce what Ray is doing? And then after the first stage, we also even continued. It was like 1.5 stage. We actually like experimented with also contest formats because we were in the innovation lab. So it's not only we want to save the world, but we also want to break the whole innovation process, like disassemble it and see like whether it still works or like where does it fail. So we will continue this challenge after it ended, like adding some different price incentives on whether you can still improve the solution, whether you want to work the solution, and testing whether the community would be interesting even to continue working on those projects. And we got that interest. And then analyzing the results of the first stage where we said, hey, just like reproduce Ray, we saw that, hey, there are examples where the results were really good. And we reproduced his segmentation extremely well. And then the results when we were completely off. And that leads to the question. So like there's something that can be significantly improved and some things are not. And that's already gives you gave us a return on return feedback on what can be improved. And we reformulated the question. So like we know that it's much easier to segment the tumor if you know where it is versus to find the tumor, because there are so many various areas that actually look somewhat the same, and they also look pretty distinct from each other. And without having an access to the complete atlas of the body and getting access to way larger data set than Ray had, we wouldn't be able to train an algorithm to be actually a doctor and to point, hey, this is like organ versus this is a tumor. We just know that, hey, there is some, but at the same time, we found that the algorithms are actually catching up pretty well on, hey, there is something going on here. Can you just segment it out? So you can do it so much better than the radiologist, and with the same precision. And so, like with some small fixes after that, that could be could streamline the entire process. And that is a really long process, as Andy already described. And
yeah,
then
I think it took almost a year.
it took almost a year to generate those images, to get his time, and to frame exactly what we are solving. And this is a part of like how the academia works, how the expertise works. So you have to be very careful, especially if you are working in the area of the healthcare. So you don't want to produce something that is poorly formulated, so you cannot defend it, and so it potentially can lead to some bad results, like in the future. So you don't want to treat those patients wrongly.
Yeah, and I guess that's Rinat, I guess that's an important thing to point out with this challenge is that from the beginning it took the point of view of being peer reviewable. That the challenge wasn't simply do something that we can eyeball and say, hey, this looks like it's pretty good. This was something which from the beginning was intended to be used therapeutically. There was no intention at all for this to be an academic exercise. One of the other participants in this, Dr. Eva Guinan, also from Harvard, is really focused on that point. It's like, let us always take from day one the point of view that what we do can be used clinically. And she runs an organization at Harvard that is aimed at accelerating treatments to take them from just an academic exercise to quickly getting them to patients so that you can extend their lives or even save them. So we probably should highlight that more, and forgive us for not doing that here. But this again, from the beginning, was how can you actually save a patient? And that's why we were so willing and able to do this, to seed the second round literally with pinpoints, right? Saying, okay, it's not just here's the cancer, here's the hollow within the cancer, and you can follow, you can contour around this, or this is a clue to where you can improve your algo. And that's why this challenge honestly was so successful because it wasn't about replacing a doctor or creating Robbie the robot that will, or the Star Trek hologram that will always be the doctor going forward. This was squarely aimed at create AI that can delineate tumor quickly and as well as leading doctors so that you can spend more time with the patient and treat more patients.
Absolutely. So from the beginning, it was a heavily peer-reviewed process when we know that the result has to be defended against like all kind of questions. So we need to know that we did it right, and we need to know that we got the maximum out of what we have. So that's why there was the stages when we framed the problems to have it right, and there were also the stages when we're trying to maximize the result, when there was the stage number 3, and there was a post the stage after the 3, when we were taking the top solutions and we were trying to ask first the crowd, and then we were working internally on like, hey, can we actually like take the best ideas out of all the top approaches and combine them and like integrate them together? And here is we also need to take say special things that we have not. I'm very sorry that we didn't say it before. So, so there was the whole project on that stage and on the later stages up to the publication was carried out by Mike Andrews, who was also data scientist at senior data scientist at our lab, and he was specifically focused on all the technical part of the projects from basically like early on to the publication of the paper. So and as always when there is a lot of like good parties like having a lot of enjoyment with the process, so the results were actually like pretty good. So like you can see some stats here on the slide. So given how much work had been done on just like brainstorming around and framework, so the $55,000 in prices, that was sort of like a part of the project, but it was a very very important part on actually like developing of the solution. And when we looked on who was participating and why they were participating, we were of course like the Harvard, so we need to ask for the motives. We need to ask for where you're from and like what you're doing and what is your background. So there is a lot of people who are from like students or postdocs from medical areas, but not only. It's from all over the world, and there is a lot of motivation for doing it not only for the prizes, but for just because they had someone, they know someone who had lung cancer, they tried to help the world, and they actually recognized that it was the project that can actually like help a lot.
So as always,
yeah.
and Rinat, let's jump into just talking about the results a little bit, and then maybe we can turn it back over to you to decompose what some of the top ranked guys are doing. Just to summarize, again, as is always the case on a Topcoder challenge, we find that the people who perform best on it are very frequently folks who don't have a whole lot of experience in the realm. In fact, I think the first lung tumor challenge was the first one that Sergi worked on. Bird of Prairie Roo, as he's known on the platform, very active in Topcoder Nation. I think this was a challenge that pulled him in. I don't know if he's on, but I'm especially glad we ran it just because of that. So we had we had about 55 grand that went out to everybody. As we mentioned before, there was a special challenge on this one in that the third round was a private invitational. In that one, we created a net zero incentive, meaning that the contestants and members were asked to collaborate. And so long as the algorithm improved the results, everyone, you get a prize. So there was no disincentive to collaborate. And there was every incentive, and the opposite was true, every incentive to collaborate. We didn't ask contestants to share their code, but we did ask them to share write-ups on what could be done, what they intended to do to improve it. And Rinat, I think you'll get into this later, but that actually resulted in like a 12% boost over the second round. And so if you were a participant in that third round, or you're interested in learning more about that, please do reach out to us. You can reach us at analytics@topcoder.com, because we'd always like to learn more and have more feedback on it. That's something we've sampled and dabbled with since then. Okay, let me tee up from the outcome point of view what the results were, and maybe Rinat, you can bring us into some details. The results are pretty clear. We'll have a second look at this again in a second, but at the bottom charts here are sketching out what the actual doctors do on the left. That's what, in this case, I think Dr. Mack sketched out as a contour. The one in the middle is what commercial software today did. Obviously, it's pretty nasty, right? That the algorithms that drive that solution today are much akin to the magic wand in Photoshop. So it's basically just doing some contour following. It's not intended to at all to replace a doc. It's just intended to reduce the amount of time they have to trace things out. That's all. And even then, it's still early, I think, in its career. The third image you see on the right is what Topcoder achieved. This is what the community achieved. It looks awful lot like Dr. Mack's. You can see there are some pretty minor differences, but that's a pretty remarkable outcome. Here are a couple other interesting things. All the top 5 solutions were 100% custom, meaning all the code was handwritten, right? There was no one was using TensorFlow. That's not true of our top 10 overall. A lot of folks in the top 10 did attempt to use open source libraries or specifically TensorFlow, but they were outperformed by our best members, our most proficient members. That said, 2 of the top 7 did use open source in some different ways, right? So I think a lot of folks use things like OpenCV to create more training data, to upsample tiles and downsample tiles and just create some messy stuff that you could relabel. So I'm not really including that. That's a data pre-processing step that helped improve the efficacy of that algorithm. But in terms of actually using it, actually using existing machine learning libraries, the folks who use them did not crack the top 5. So it was pretty cool. Of course, the overall outcome here was job well done. The algo actually does perform well enough that the team is starting to move forward with what the next step might be. Okay, so let's get into some specifics of the result here. We'd like to talk a little bit about the techniques used. So Rinat, do you mind taking it away from here?
Absolutely. So first of all, the whole idea of how we use the multiple challenges was to actually compare a lot of techniques and do a lot of peer review of those techniques. So we can actually select the techniques who are the best, implement them in the best way, and combine the ideas from multiple techniques together. So as you see on the left table, so that's a list of the top techniques that had been winning the contest, phases after phases after phases. So the first, so there was random forest, there was the neural net, convolutional neural networks, and cluster growth. So most of that was more or less staying on the top. The challenge after challenge, there was some shuffling in the placements over the contest, but at the end it resulted in actually combining most of those techniques together, and the final solution that we had was actually a combination of the random forest and the signet convolutional neural networks, which allowed to improve improve the performance for a little bit more. And uh, but what I wanted to emphasize here is that Topcoder is like when we create the challenge and you have a competition and the best coders are fighting with the best coders on developing something better and better and better. So the idea of, hey, we improved it by something is somewhat very obvious. Like, yes, that's sort of like the whole idea of the competition. Much harder question is whether the result is actually good. So what can you compare, whether we actually help the world or whether we can actually improve the results? And this is like way much harder question that if you could think, because you have to compare it with something. So like first you can compare it with the Ray segmentation by himself. But then there is a question like, whatever, even the best, the perfect algorithm in the world, even like the algorithm that would be better than Ray in segmenting the tumors, would probably will never exactly reproduce the Ray segmentation. So it would be always like some errors, and most of them would be like actually Ray's errors. And first we took his data set as like the perfect data set that we have. And then we had actually like a question, so what do we do? Like what if the performance becomes actually comparable to what he is doing? So how can we benchmark like where would be like a good result, a great result, and a perfect result? And we did a couple benchmarks. First, we picked a few methods that Ray would use in his life. And one of them was very simple than we have shown before in the middle slide, where that was basically like a Photoshop type of segmentation. And we in the middle, and we tested that on the data set within the same like scoring system, how close it does reproduce the race images. And the second one was actually using some machine learning, and that was the software that was actually available to him. Was it actually like the top world software? No one knows, because there is a lot of commercial softwares that are hard to test, but this is exactly that he would use. And that created like two benchmarks, like just on how close those methods were producing his results. And on the first challenge, we actually surpassed the first benchmark, which was great. And then we saw that, hey, we have great results and then we have poor results, and we can reformulate the problem. So we use actually the strong sides of the algorithm. And we can also improve some, implement some suggestions from the winners, because in the descriptions, there was a lot of feedback of how to improve the solution.
So Rinat, I think what you're saying is from the first challenge, we took the write-ups and learned from them along with the counterfactuals that you did, and took that forward into the second challenge.
Right, and if you use actually, and if you look where the results are on the second challenge, where the results from the first challenge were open, so they already were higher than the second benchmark. So we already surpassed what the Ray could use as a software. So the second question is, so like if you're better than any software, like what is that next kind of like level we could compare? So the next level could be compared would be like the Ray himself. And that was a big challenge. How can we like sort of figure out where would Ray make a mistake? And we did it actually, so first we did it by chance. We had no idea like how to do it, because there was a lot of innovation in this project. And first we did it by chance. So when Mike Andrews was working with Ray, he was sending him like, here is like 20 scans, here's 100 scans, like here is like another 20 scans. Can you like segment them? And at some point, he just made a mistake, and we sent him already like a bunch of the scans that he had already done, but long time ago. And we annotated them without actually remembering, because he's doing so many of those scans like in his real life. So he annotated them without even remembering that he had been doing that. And we could actually compare how accurate is Ray on Ray.
So by a happy accident, we sent Ray sections he had seen before, but forgot that he segmented. He re-segmented them, sent them back, and then we saw that the second effort was different in many ways from the first effort. And that allowed us to go into the second challenge to
And the results were different.
Wow. Yeah, I don't think I knew that one. So that's what allowed us to say both, here's how there's drift among the same physicians. And so it isn't just theoretical, you can actually see it. And then did that become input to how the second challenge was designed, or was that more for third challenge?
That was already for the third challenge, because as soon as we are better than the existing benchmarks, so sort of like the first goal of the second challenge was already achieved. So we already improved something, but we still don't know how valuable it is for the global world. So whether it is still going to be a toy software to just help that Ray cannot trust and the radiologist cannot trust, or can we actually get somewhat like comparable to what the radiologist can do? And that was and for that it was first extremely lucky, and then we kind of like did it on purpose. We saw it like a little bit more like similar scans and like tested his error, and we figured out no, like non-radiologist is perfect. So when you see that intra-observer benchmark on the right plot, you can see it's all around like 75 to 80%. So 75 to 80% is an average overlap of a great radiologist and great radiologist, which is actually not that huge if you think about it. There is
No, it's a little scary, actually.
It's actually scary. It means like how many questionable areas where even radiologists don't know whether to include them or exclude them. And then you cannot even criticize an algorithm when they, for example, include it versus like radiologists right now exclude it, or other way around. So
Rinat, we're coming up with about 10 minutes left in the session. So I just want to break in for a second to remind folks, if you're online and you'd like to ask a question, please do. Put it into the chat, into the Q&A, and Harshit will read it out while we continue this discussion. So going back to the results, Rinat, let me summarize and see if we're about the right spot here. At the conclusion of the second round, we'd already demonstrated that it's better, or actually the conclusion of the first round, we already showed that we're better than the Topcoder solutions already showed that they were better than the commercial solutions that were out there. Out of the second round, we aimed at least matching Dr. Mack himself. In the third round, we began to explore how we could even do better than that. And the result of the third round was a solution that performs about as well as can be explained by medical doctor proficiency. There's maybe a little bit of room to improve, but beyond that, we're really into a gray area where the leading experts themselves don't agree as to whether or not a specific group of pixels should be included in the contour. Is that an accurate assessment?
Yes, that's quite accurate assessment, because like first we figure out like how often even the great expert makes mistake on his own like judgments. But then we also added the other radiologists and compared that and start comparing them with each other. And we figure out that, hey, actually like what we got out after the third round is exactly like in the area where the radiologists just disagree.
Wow. I recall that coming up in the setup, but I don't think I appreciated how close we got to that threshold, and that probably even bleeds left a little bit, where Ray maybe is not making the same choice each time.
So we still probably a little bit worse than Ray, but we are better than we are about to be as good as a good radiologist, because Ray is phenomenal radiologist.
So we're just a little bit shy of one of the top 5 physicians in the world. But so I guess in Topcoder land, our algorithm would score about yellow as a physician, and maybe not quite red, or maybe red, but not quite CIHO uh, performance quite yet, but close. So if good point here to pause this for a second and say, if you were a contestant on this challenge, you should know that you were part of the solution for something that hopefully really will be used in the world. We think this in treating patients, because it's easy to think 30 to 60 minutes isn't so long. A doctor spending that amount of time on a scan doesn't seem like that long. Truth is, it's a really long time. The less amount of time you can have a doc doing tasks like that, the more time that doc has in spending time with that same patient or seeing more patients. And there's a backlog for being able to see doctors for something like this. And it's especially bad for aggressive tumors like lung tumor, like pancreatic tumor, things like that, because from the time from diagnosis to death isn't great. The 5-year survivability of these tumors is really low. So it's super, super, super important to be able to see that doctor right away. And if you think a little bit further into, maybe what would have been sci-fi realm even 5 years ago, which is just maybe now today in the work from home world and a COVID affected world, telemedicine is everything. You have so many elective surgeries right now, so-called elective surgeries and treatments that have been benched because people can't go into clinics. It's impacting life-saving methods as well. So the more you can build automation into these things, and you can move treatment away from centers and to the edge, even in walk-in clinics, the more people you can treat and the more people you can save. So if you contributed to this, congratulations. You should be proud of what you did. Everyone who contributes puts a dot on the leaderboard. Every dot on the leaderboard makes it harder for the leaders to win. And the harder you make it for the leaders to win, the better the result is. And in this case, that means better treatment for a patient. So congratulations, and obviously thank you for participating. If your interest in joining this is to learn more about the solutions themselves, I think a lot of these assets are available as part of the academic paper that was published on these. We'll be sure to share the link in the follow-up and in the forums. And I think we have some Thrive material slated for this to come forward. We are not at this time, I think, posting the solutions themselves because they were part of an academic study. But if you have interest in the approach, please do reach out to us and we'll figure out what we can share. But that's why we like this chart. This chart and many others are available on the JAMA article. You can see all the breakdown of the individual solutions and how they performed. You can see how the results changed for each of the 3 rounds. And there's also some information in there more broadly about the problem. So please do jump in. So I think we're down to our last few minutes here. So Rinat, let me turn it back over to you for any closing remarks or observations that you'd like to share.
Thank you. So thank you so much so first of all, thank you for all the partners who participated on this project. So for Topcoder, who was so flexible to it, and that allowed us to experiment with all the approach, and to figure out, we had to actually feel where can we improve it, and where the improvement is possible, where the breakthrough is possible. And there was a whole methods how we try to implement in an innovative way how to feel and how to find the right spot. So, and the Topcoder structure that running the kind of getting feedback, running it again, calling the members, inviting the members. So that allowed us to implement that innovative structure of the development. So that's really the result of collaboration of the multiple worlds that worked pretty well.
this is easily one of my favorite, my top three for me, favorite challenges and solutions in my Topcoder career. So this was awesome. Thanks again to everybody who made it possible.
And yeah,
sorry, go ahead.
What are the other two favorite of your? What are the other two projects?
I knew you were going to put me on the spot, man. Stay tuned for future webinars.
Awesome.
I don't want to discourage anybody, but I'll just broadly say that they may have been space related.
Okay.
And it may be that I know them too.
They're tall, really tall. I'll name one of them. I'll split the difference with you. One of them obviously was the Longeron challenge. You know, a long time ago now, like 2013. But that sucker was both extremely difficult to host and even more difficult to solve. And the results came back were just awesome. And so maybe that's a good parting thought. If you are a contestant on Topcoder, you know, you've gone through a lot of experiences with the platform and with test harnesses and scoring. What this hopefully has given you a good view of just how much the actual contest that gets posted is a tip of the iceberg of the usual problem that we solve. In this particular problem, there were literally months, almost a year, of effort that went in upstream of posting the contest. That involved a lot of discussions about how things should be scored. It involved, you know, preparing the data, deciding what should go into that data. I mean, I think that data set actually had over 600 scans, and we ended up with those 429. I mean, there were conversations that went into that. The Longeron challenge is the same thing. That was a good almost 6 months of iteration, figuring out the right way to just host the darn thing. So we hope you enjoy them. We love posting them, so look for more.